Look up at Orion on any clear winter night. Find the hunter's right shoulder, that warm, smouldering orange ember burning against the black. You've probably seen it 100 times without really looking. Tonight, look closer, because what's sitting up there is not behaving the way a star should behave. It is not doing what the physics textbooks said it would do, and in late 2019, it did something so unexpected, so deeply wrong by every model astronomers had built, that telescopes all over the world stopped what they were doing and turned toward it. By January of 2020, a star that human beings have been watching for thousands of years had lost 2/3 of its visible brightness, and nobody could explain why, not with confidence, not without fear sitting quietly underneath the science. That's the thing about Betelgeuse. It has always been there, steady, ancient, reliable in the way only the night sky can be reliable, and then, without warning, it started to vanish. What followed was one of the strangest episodes in modern astronomy, and buried inside the data, inside the brightness curves and the spectral readings and the imaging we collected during those frantic months, there is a detail, a possibility, something that astronomers are careful to phrase in the most cautious possible language, because the alternative, saying it plainly, feels almost too large to say. We'll get there, but first, we have to understand what Betelgeuse actually is, because it is not what most people think it is. If what you just read made the hair stand up on the back of your neck, you're exactly where you should be. Subscribe if you want to keep going deeper. We do this every week. Betelgeuse sits roughly 640 light-years from Earth, marking the right shoulder of the constellation Orion. To the naked eye, it ranks among the brightest stars in the night sky, usually inside the top 10, depending on where it is in its brightness cycle. But the first thing you notice, if you really look, is the color. Most stars from our perspective look white or blue-white. Betelgeuse does not. It glows red-orange, the color of cooling iron pulled fresh from a forge, the color of a fire that has been burning for so long it is finally beginning to wind down. That color is not decoration, it is a clue, and it tells you something important about what kind of object you're actually looking at. Color in stars is a direct measure of surface temperature. Blue and white stars burn hot, tens of thousands of degrees on their surfaces, and they burn fast, living brilliantly for only a few million years. Red stars run cooler, around 6,000 degrees Fahrenheit at the surface, and they come in two very different varieties. They are either very small and extraordinarily stable, burning at low temperatures for billions of years with patient, quiet efficiency, or they are very large, very evolved, and fundamentally unstable. Betelgeuse is the second kind. Betelgeuse is a red supergiant, and that word, supergiant, does not come close to preparing you for the reality of what it means. If you pulled the sun out of the center of our solar system and replaced it with Betelgeuse, something extraordinary and terrible would happen. Mercury would be inside Betelgeuse, Venus would be inside Betelgeuse, Earth, with its oceans and its continents and everything that has ever lived on it, would be deep inside a sphere of churning, glowing plasma, submerged beneath hundreds of millions of miles of stellar atmosphere that would continue expanding outward past Mars, past the asteroid belt, and depending on which size estimate you trust, reaching somewhere between 2/3 of the way to Jupiter and beyond Jupiter's orbit entirely. Stand outside on a clear night and hold that image. A single object so enormous that if you placed it in our cosmic neighborhood, you and your house and the entire planet would be inside it, not near it, inside it, with the outer edge of the thing still millions of miles above you in every direction. That is what is hanging in Orion's shoulder, quietly, every winter, and it is not at rest. Betelgeuse heaves, it pulses with slow, irregular rhythms, its surface boiling like an ocean in a storm, except the waves are thousands of miles high, and the ocean is made of plasma. Convection cells, enormous bubbles of hot gas rising from the interior, are each roughly the diameter of the distance between the Earth and the Sun. They rise, they cool, they sink, they rise again. The surface of Betelgeuse is not a place of stillness. It is a place of constant, immense turbulence, and it has been that way for hundreds of thousands of years. There is no version of Betelgeuse that is calm. There never has been. What you're seeing when you look at it is a star in its death throes, just playing out over a timescale so vast that no human lifespan can register the change. Or so we thought. In October of 2019, astronomers started noticing something in the data. Betelgeuse was getting dimmer, not in the gradual, cyclical way it always dimmed. It had a known brightness cycle of roughly 400 days, and longer overlapping cycles layered on top of that. but faster than any of those patterns predicted. By December, the drop was impossible to ignore. By January and February of 2020, Betelgeuse had lost approximately 2/3 of its visible brightness. If you stood outside that winter and looked up at Orion, something was wrong. You didn't need a telescope or a chart or any astronomical training to feel it. The shoulder of the hunter was dim. It was the wrong color, the wrong magnitude, the wrong presence. The constellation looked broken. Nothing in the known behavior of Betelgeuse, not the 400-day cycle, not the longer cycles, not any combination of them running simultaneously, could account for what was happening. The astronomical community did something it rarely does so visibly. It panicked, productively. Papers were rushed through in days rather than months. Observatories redirected their instruments. Theorists worked the problem from every angle. And the theory that spread furthest, the one that lit up every science news site, every astronomy forum, every dinner conversation, was simple and enormous. Betelgeuse was about to explode. A red supergiant does not live forever. It burns through its fuel in stages, fusing heavier and heavier elements in its core as lighter fuels are exhausted, until finally, when the core has become iron, the one element that cannot be fused to release energy, gravity wins. The core collapses in a fraction of a second. The outer layers fall inward, hit the rebounding core, and are blasted outward in a shockwave moving at thousands of miles per second. The explosion briefly outshines an entire galaxy. Astronomers have always known this was coming for Betelgeuse. The physics are unambiguous. The question was only ever when. And in February of 2020, watching that ancient red light fade out of the winter sky, when began to feel uncomfortably like soon. People went outside and looked up. Not astronomers, ordinary people. They stood in their driveways and their backyards and their apartment balconies, and they looked at the dim shoulder of Orion the way you might look at something you are not quite ready to lose. There is a particular feeling that belongs to witnessing something ancient approaching an ending. That feeling was in the air that February, sharp and strange, the way it is when you know a change is coming and there is nothing to do but watch. Then Betelgeuse came back. By April of 2020, its brightness was recovering. By summer, it was back within its normal range. The Death Watch, as the internet had started calling it, was over. But the question of what had actually happened was not closed, it was only just opening. The data collected during those months, the spectra, the brightness curves, the imaging, contained a problem. Not a mystery in the sense of something unknown, but a specific, technical, deeply uncomfortable mismatch between what the standard models of stellar behavior predicted and what had actually been observed. The dimming was real. The cause needed to be real too, and it needed to be something the physics could account for. Two explanations emerged as leading candidates, and the truth turned out to be both of them simultaneously, working together. The first was a cold spot. Betelgeuse's surface is not uniform. Those vast convection cells rise and fall at different rates in different regions, and it was possible that one of them had surged up, lost its heat rapidly, and produced an enormous patch of relatively cool, dim stellar surface facing directly toward Earth. A single region of the surface cooler than its surroundings, even if it covered an area the size of multiple of our suns, would dim the star's apparent brightness from our viewpoint without changing anything about the star's actual energy output. It would be like a bruise on a piece of fruit, local, real, and not necessarily a sign that anything catastrophic was coming. The second explanation was dust. Red supergiants are notoriously messy objects. They shed material constantly, bleeding their outer layers into the space around them in a slow, continuous wind of gas and plasma. When that material cools far enough from the star, it condenses into fine grains of silicate dust. If a thick enough cloud of that dust formed between Betelgeuse and Earth at exactly the right moment, it would block light without the star itself doing anything unusual. The star behind the dust cloud could be fine. We'd just be looking through a curtain. By 2021 and 2022, teams working with the Hubble Space Telescope and a coordinated network of ground-based observatories had assembled the pieces. What they found was this: a massive plume of plasma, hundreds hundreds of times larger than anything our sun has ever produced in a recorded solar flare, had been violently ejected from the surface of Betelgeuse. As that material traveled away from the star and cooled, it formed a dust cloud, and the region of the surface that had launched the ejection was left cooler than its surroundings. We had been looking at the worst possible angle through a freshly formed dust cloud at a cold spot that the ejection itself had created. Both things were real, both were connected. Both together explained the magnitude of the dimming. This should feel like an answer. It is not quite, because it immediately raises a harder question. Why? Red supergiants shed material, they always have, but they do not normally launch a single eruption equivalent to several times the mass of the moon in a matter of months. Something had driven that ejection, something moving beneath the surface, something that the standard models, the clean, smooth, peacefully aging picture of how a star like Betelgeuse was supposed to behave in this phase of its life, had not predicted. And as more data accumulated in the years that followed, the picture did not simplify, it got weirder. Fast forward to 2023. Betelgeuse was doing something new. Its brightness had begun oscillating on a cycle that did not match any of its known patterns. A new pulse appeared in the data, faster than the familiar 400-day rhythm, with a characteristic shape that drew the attention of a specific group of researchers. The ones who had been quietly watching an old problem that nobody had managed to solve. For decades, telescope observations had been flagging something strange about Betelgeuse's rotation. Red supergiants are slow rotators by necessity. The physics works like a figure skater extending her arms. The larger the object, the slower the spin. Betelgeuse, scaled to its enormous size, should rotate very slowly. The measurements said it didn't. The measurements, going back many years, showed it spinning at speeds that had no obvious explanation from normal stellar evolution. Astronomers had a name for this. They called it the Betelgeuse rotation problem, and for a long time the leading explanation was, essentially, that they were misreading the signals. The violent surface convection, they reasoned, might be mimicking the appearance of rotation in the data. It was a theory of polite denial. The math doesn't work, therefore the data must be wrong. Then a different theory began to gain traction, quietly at first, then with increasing confidence. What if Betelgeuse was not alone? What if, hidden somewhere in the overwhelming brightness of one of the largest stars visible to the naked eye, there was a second object, a companion star, orbiting close, lost in the glare for the entire history of human astronomy? The idea wasn't new. Binary and multiple star systems are common in the universe. A majority of stars have at least one companion. What would be remarkable wasn't the existence of a companion, it would be the fact that we'd been looking at Betelgeuse for millennia without noticing one. The hypothetical companion got an affectionate nickname, Beetle Buddy. The name is cheerful, what it would imply for Betelgeuse's future is not. If a companion existed in close orbit, it would explain the anomalous rotation. A companion transferring angular momentum could spin Betelgeuse up over time. It might also explain the strange new oscillation patterns appearing in the 2023 data, and it would fundamentally change every model astronomers had built for predicting when and how Betelgeuse would eventually die. For years, Beetle Buddy lived only in the mathematics, a ghost assembled from light curves and subtle spectral variations, with two competing research teams predicting slightly different masses and orbital periods, neither able to pin it down to a definite observation. The problem was simple and brutal. Trying to spot a companion star next to Betelgeuse is like trying to see a candle flame held beside a stadium floodlight from several miles away. The contrast is so extreme that normal imaging simply fails. In December of 2024, a team led by Steve Howell at NASA pointed an instrument called Alapeque at Betelgeuse. Alapeque is mounted on the Gemini North Telescope on Mauna Kea in Hawaii, and it was designed for precisely this kind of challenge. It captures thousands of ultra-fast snapshots in rapid succession, each exposure lasting only 1/100th of a second, then stacks them computationally in a way that cancels out the blurring caused by Earth's turbulent atmosphere. The final image approaches the theoretical physical limit of what the telescope can resolve. The team chose their timing with precision. If Beetle Buddy existed and followed the predicted orbital path, December 2024 was the moment it would be at its greatest apparent separation from Betelgeuse, the widest gap the cleanest window, the best chance any astronomer would get. For comparison, the same instrument had been pointed at the same target back in 2020, during a phase when the companion should have been hidden behind the supergiant from our line of sight. The 2020 images showed nothing. The 2024 images were different. There was a dot, faint, slightly bluer in color than Betelgeuse, sitting at exactly the predicted angular separation and position. After decades of mathematics and inference and polite argument, Betelbuddy was real. Follow-up observations in X-ray and ultraviolet, released in 2025, refined the picture further. The companion is a young star, approximately 1.5 times the mass of our Sun, and it appears to be a pre-main sequence object, meaning it has not yet begun fusing hydrogen in its core. In stellar terms, it is an infant, and that infant is orbiting close enough to Betelgeuse that it is not merely near the supergiant's atmosphere, it is embedded inside it, drifting through the outermost wisps of gas at densities 100 times thinner than the air in your home. This is not a stable arrangement. The companion is being dragged through Betelgeuse's atmosphere with every pass, bleeding orbital energy through friction, spiraling slowly, inexorably inward. Estimates place the merger tens of thousands of years away. When it happens, Betelbuddy will fall entirely into Betelgeuse, possibly contributing the very angular momentum that has had the supergiant spinning too fast for so long. The next window to observe the pair closely comes in November 2027, when the companion swings back to its maximum separation, and by then, astronomers expect to have a sharper portrait of what this young star is actually doing to its enormous, dying neighbor. All of which brings us to the part of this story that does not stay in the textbooks. The reason Betelgeuse keeps surfacing in your newsfeed, in the texts from friends who haven't thought about space since high school, in the quiet, late-night searches that end in someone staring at a star map at 2 a.m. Betelgeuse is going to explode. Not as a theory, not as a possibility, as an inevitability written so deeply into the structure of physics that there is no universe in which it does not happen. Any star between roughly 10 and 20 times the mass of our Sun will, at the end of its life, exhaust the fuel in its core, collapse under its own gravity, and detonate. Betelgeuse sits in that mass range. The fuel is almost gone. The clock is running. The question is only the word almost, because in stellar evolution, almost can mean tomorrow, or it can mean 100,000 years from now. Recent papers, built on the strangeness of the past 5 years, the 2019 ejection, the new oscillation patterns, the confirmed companion, have argued that the window may be tighter than older estimates suggested, perhaps tens of thousands of years rather than hundreds of thousands. A small number of researchers have gone further still. They have looked at the violence of the surface mass ejection, the behavior of the new pulses, and the implications of a companion spiraling inward, and they have quietly raised the possibility that Betelgeuse may be approaching the final phase of core silicon burning. That is the last stage of stellar nuclear fusion before collapse. It lasts, depending on the star's mass and conditions, a matter of months before the end. This is almost certainly not what is happening right now. The overwhelming consensus is that Betelgeuse has thousands of years remaining, probably far more, but almost certainly is carrying a lot of weight in that sentence. And the honest thing to say is this: nobody has ever watched a red supergiant in the days before it died. Nobody knows what the actual warning signs look like, because every supernova we have ever studied was discovered after the fact, when the light from the explosion reached us. We have no playbook for this. We are writing it in real time. When it goes, whenever it goes, the event will be unlike anything in recorded human experience. The light from the explosion will reach Earth as a sudden, impossible brightening of a single point in Orion. Within hours of first detection, Betelgeuse will be visible in broad daylight. A hard, blue-white spark hanging in the sky where the familiar red shoulder used to glow. It will outshine the full moon. It will cast shadows on clear nights. For roughly 3 months, it will be the second brightest object in the entire sky, behind only the Sun. Then it will begin to fade, slowly, over the course of a year or so, the color shifting, the point of light shrinking back toward the brightness of ordinary stars. And when it is finally gone, the constellation Orion will be permanently changed. For the rest of human history, however long that turns out to be, Orion will be missing a shoulder. Every person who ever learned those stars as a child and looked for them on camping trips and pointed them out to their own children, all of them will look at that corner of the sky and notice the absence and know what it means. What will remain, sitting silently in the space the supergiant occupied, will most likely be a neutron star, one of the universe's most extreme objects, built when gravity compresses the collapsed core of a massive star so completely that individual atoms break apart. Electrons are forced into protons. The entire remnant becomes a sphere of pure, tightly packed neutrons, roughly 12 miles across, approximately the length of Manhattan, with a surface gravity more than 200 billion times stronger than Earth's. A teaspoon of neutron star material would weigh approximately 1 billion tons. It is matter pressed to the very edge of what matter can be before it becomes something else entirely. And in some scenarios, depending on the angular momentum of Betelgeuse's core at the moment of collapse, and possibly influenced by the energy contribution of its now confirmed companion, the remnant might not be a neutron star at all. The collapse might go all the way. Betelgeuse, in its final moment, might compress past the neutron stage into a singularity. The supergiant in Orion's shoulder might become a black hole, and we would watch it happen, standing in our backyards in the dark, with no idea until the light arrived. You may be wondering whether that much energy, that close, poses any danger. It's a fair question, and the honest answer is almost certainly not. 640 light-years is genuinely far. The most lethal effects of a supernova, the destruction of the ozone layer by intense radiation, the stripping of the upper atmosphere, reach out only about 30 to 50 light-years from the source. Betelgeuse is more than 10 times beyond that range. The radiation will arrive too thin to do biological harm. There is one exception worth understanding: a gamma-ray burst, a focused beam of radiation produced when a dying star's core collapses while spinning so fast that the resulting jets are channeled into narrow beams along the rotation axis. If one of those beams pointed directly at Earth, the effects could reach across the galaxy, but gamma-ray bursts require very specific stellar conditions, particularly Wolf-Rayet stars with extreme angular momentum and unusual chemical compositions, and Betelgeuse does not meet those criteria. The consensus is that when Betelgeuse goes, it will produce a standard Type II supernova, spectacular, violent, and completely harmless to life on Earth. The neutrino pulse will pass through the planet and through your body, but neutrinos barely interact with matter at all. You won't feel anything. There might be a brief increase in auroras at high latitudes. Pilots would notice, most of us would not.